Okay, hello everybody. My name is Alexander Kamkin. I'm from Ivanikov Institute for System Programming of the Russian Academy of Sciences, or just Institute for System Programming, or simply ISPROS. So I'm going to talk about Machine-Readable specification of RISC-V instruction set architecture, about motivation for formalizing RISC-V architecture, about our approach, tool that we use, and application we are currently working on at ISPROS. Okay, what is the main reason for formalizing a computer architecture? The main word here is automation. Formalizing microprocessor architecture allows us to automate lots of activities, including CPU design itself, cross-tool development automation, and of course, different kinds of verification. So all of you have heard about high-level synthesis, where high-level behavioral or algorithmic description is translated into synthesizable RTL, Verilog or VHDL. So a good example is a Clash tool that translates Haskell description to synthesizable RTL description. So many tools, including simulator, compiler, assembler, disassembler, can be automatically generated from instruction set description, from formal description. And there are many tools that automate that activity. And for example, CodaCeep Studio based on Codal language. And we also do some kind of research in that area. And of course, formalizing architecture allows automate different kinds of verification. Functional verification, security verification, verification of hardware, and verification of software. And here are just a few examples of specification-based verification techniques. Test program generation, equivalence checking, theorem proving, and binary code analysis. So in my talk, I will focus on Microtask. It's a framework developed at ISPROS, and in particular on two applications of that framework, on test program generation and binary code deductive verification. RISC-V, I think, is the only architecture that pays so much attention to formalization. There are lots of activities in the area, including technical activities and research activities, and there is no clear borderline between technical and research activities. So technical activities mostly use some traditional approaches like programming languages, because instruction set simulator developed on some programming language is a formal description of instruction set architecture. So also some ISA-centric architecture description languages are used. For example, NML language we use in our group, or Codal, and some others. And also high-level hardware description languages, high-level HDLs, like Chisel, BlueSpec System Verilog, etc. Research activities mostly concentrated on some science-intensive approaches and more science-intensive languages, in a sense. For example, on functional languages, like Haskell, first of all, and ISA-centric architecture description languages, and also logic frameworks like COC, PVS, Y3, and others. Being open architecture, RISC-V needs some open source projects and some open source specifications of instruction set architecture. And here's a list of some open source projects related to RISC-V formalization. So let me not dwell on all of them. I think slides will be publicly available. The last item is our specifications in NML. So yes, we use NML. NML is ISA-centric architecture description language developed in the early 90s at Technical University of Berlin. It's a rather old language, but in our opinion, it's quite flexible for our applications. So specifications in NML are translated into so-called processor model. Processor model is quite a complex and sophisticated structure. It's not a monolithic one. It consists of several components, including metadata, which is syntactic information about microprocessor instructions and registers, some simulator, which is built-in interpreter of microprocessor instructions, and so-called coverage model, which represent execution passes extracted from specifications. And they are represented in terms of constraints to be used, for example, in test generation. to direct test program generator in some particular corner cases, in some particular situations. Okay, and processor model is shared among different engines, including test program generator, symbolic executor, and different builders that can construct another representation of formal specifications, including simulators, some probably logical specifications to be used for formal verification, and so on. So test program generator is the original and the main purpose of microtask. And by the way, microtask stands for microprocessor specification and testing kit. So test program generator analyzes specifications and able to produce test programs in assembly language, either random or directed one, using user-specified, user-defined verification scenario. A symbolic executor takes binary code, decodes it, and produces some formula, some in asymptotic representation that describes program execution in a formal way. And as I said before, builders can construct different representation of ISA specifications. So as I said before, there are different activities in the area. There are different specifications in different notations. And a very important issue, how to make sure that specifications are valid, how to ensure consistency between different specifications. We use testing-based approach. So we can generate test programs by using microtest test program generator and then execute them on a reference simulator. We use QEMU for RISC-V. And so in a sense, we check that built-in simulator constructed from a specification is consistent with the reference instruction set simulator. And so that makes us confident that we use valid specifications. And here is how NML specifications look like. As you can see, we can specify constants, we can specify data types, interpreted as, it's bit vectors interpreted as signed or unsigned integers or floating point numbers. We can specify access modes, addressing modes, which describes how to access the registers and the memory. And we can specify operation. And here is, for example, the add operation. So as you can see, we can specify assembly syntax, we can specify binary encoding, and we can specify semantics. And the same is applicable to addressing modes. We can also specify assembly syntax, binary encoding, and semantics, how to access the registers and the memory. The language supports so-called and or rules to compose complex operations from simpler ones, and that makes us possible to specify complex instruction set architectures, including CISC and VLIF architectures. So the language is rather powerful. Unfortunately, it's not powerful enough to describe memory management. And for this reason, we have introduced our extension of the language called MMUSL, Memory Management Unit Specification Language. So that language allows to specify, it's not shown here, allows us to specify address types, virtual addresses, physical addresses, probably intermediate addresses, address spaces, which describes mapping of, for example, physical addresses to virtual addresses, buffers like TLBs, page tables, cache memory, etc. And of course, overall memory access logic. So what happens when a single load or store instruction accesses the memory? And by the way, we haven't specified memory management for RISC-V as one of the future work directions. So this slide shows statistics on RISC-V specifications in NML. We have specified standard subsets, except for 128-bit arithmetic. It's not a problem, just lack of time. And we have specified some standard extensions, including M, multiply, and division, A, atomic instructions, S and D, single and double floating point operations, and C, compressed instructions. So again, memory management hasn't been specified so far. It's one of the future work directions. Now, I'd like to say a few words about applications of specifications of RISC-V instruction set architecture we are working on at our institute. So the first application is architecture level verification. So in here is the basic scheme of test program generation and test program based verification. So we have test programs in assembly language, and test programs are executed on design under test, RTL model, FPGA, or integrated circuit if we're speaking about post-silicon verification, and on reference simulator, QEMU, Spike, whatever. Both design under test and reference simulator produce execution traces, which are sequences of events stored in files, so in memory, if we're talking about on-the-fly trace matching. Traces are compared with trace comparator, and the result is verdict, either positive if trace match each other, meaning that no bug is detected, or negative. In this case, we need to determine which of the components need to be fixed. There is an alternative scheme where no reference simulator and no execution traces are used. In this case, we use test programs with self-checks. And the main question here is what's inside that left box, that box on the left. So in other words, how to automate test program generation. We use an approach called specification-based testing. So the idea is not new. The idea is to separate architecture-dependent knowledge from architecture-agnostic test generator. And I think originally this idea was implemented in test program generator Genesis Pro in IBM Research. And we basically follow that concept. Of course, we have some distinctions. Specifications in NML translated into the model. And again, model consists of several components, including metadata, simulator, and coverage model. Another input is so-called test template. Test template is a description of verification scenario. It's written in Ruby-based domain-specific language. It's analyzed by test generator. So test generator analyzed process test template and generates set of assembly programs. It's compilable assembly code together with a linker script. Generally, it works good, but we want more automation, and we want some test templates to be generated automatically. And for this reason, we have introduced a component called aftergen. Aftergen analyzes the model and produces test programs automatically. Of course, so-called architecture validation suite. Of course, it's not a complete set of tests, so it's insufficient for high-quality verification, and verification engineers still required. But nevertheless, it automates some routine verification tasks. So it's a kind of push-button technology for simple tests. And here is a simple test template. Test template is a Ruby class. It describes prolog and epilogue, not shown here, and set of test actions. A test action is a sequence of instructions. And to describe sequences of instructions, you can use assembly-like syntax. You can use Ruby constructs like conditional and loop statements to control instruction stream generation. And you can use special constructs like blocks and situations. Now, block allows us to construct complex sequences of instructions from simpler ones by combining and merging them, and situation are just references to the coverage model. It's references to constraints that allows us to direct test program generation to some particular corner cases. And this example describes a Cartesian product of two sets of instructions. Each set consists of two instructions, so there are 4 test cases. Here is an example of test case on the left. It consists of test action, 2 instructions, and an exclusive OR, and initialization code that puts generated test data into the registers. And it should be emphasized that microtasks include test templates that cover tests from RISC-V foundations, and it also support test templates, contains test templates that are able to generate test programs similar to ones being generated by Torture. One important note that microtask is open source, is generated under Apache license version 2, so you can download it and use it for free, no restrictions. It doesn't matter if your project is a research one or commercial one. So please try to use it in your projects. And another application is binary code verification. So we at ISPROS involved in operating system development, including real-time and safety-critical ones. And the key components of operating systems need to be verified formally. We use deductive verification, so the goal is to verify total correctness of a component against pre- and post conditions. So when we use classical approach based on Floyd, Hoare, and Dijkstra methods, we use from-a-C, a platform for static analysis of C code, in conjunction with the Jessie plugin, which in turn uses YML language and Y3 deductive verification platform, and generally it works good. Safety-critical components, it's not enough to verify safety-critical components on source level only. Because, you know, two reasons are that compilers are not free of bugs, and programming languages are not fully specified. There are some implementation-defined holes. So, and we suggest verifying them at binary code level. Microtask decodes the binary, extracts the control flow graph, and annotations. And yes, so we have source code in C programming language annotated with ACSL, ANSI specification language. So we translate that code into the binary, and annotations are transformed accordingly. And so then we have a binary, and we have annotations reformulated at the architectural level. So in terms of some architectural elements, registers and memory locations. So after that, microtask decode the binary, extract the control flow graph, and formulates verification conditions, and then tries to prove or refute them by using SMT solvers like TAT3, CVC4, etc. So that's the main idea. And this work is in progress. Not all of the steps are fully automated, but it works, and we use that approach in some of our research projects. And the next slide is just to feel the flavor of architecture-aware deductive verification. So we have source code annotated with ACSL assertions, preconditions, loop invariants, loop variants, some inner assertions. Code is translated into the binary. Annotations are transformed accordingly. Then we formulate verification conditions using the classical Floyd approach and try to prove or refute them with SMT solvers. So to conclude with, our motivation for RISC-V formalization is rather clear. It's nice to see lots of activities in that area. And we are doing our part of the job. Not all of our work is automated, so some things need to be improved. RISC-V specifications. We are going to specify 128-bit arithmetic and the remaining subsets, some standard extensions. Yeah, we want to specify memory management, and I don't know if there are improved specs available. Speaking about microtask framework, we're thinking on online test program generation and post-silicon verification. And also we're interested in RTL generation. So what we want to do is to generate synthesizable RTL from NML specifications. So idea is not to produce some optimized design. The idea is to obtain something to be used as a reference model for equivalence checking. And yeah, specification validation. So as I said before, we use a testing-based approach, and we still need to improve coverage analysis and automatic test generation. And we're thinking on formal equivalence checking. So I think it's a promising idea to use high-level synthesis to synthesize different high-level specifications to RTL, and then check their equivalence by using some conversion techniques like bounded model checking. Here are our contacts, the website, the email address. So we are open for collaboration. Feel free to contact us. Again, Microtask is open source tool. You can download it and use it for free. And thank you very much.